Classical mechanics, we're talking about work energy, we're talking about line integrals, and I want to do 3 examples of line integrals around a closed path. And that's important. Because let's just consider a very generic case. So we have the following. We know that we define work as the path integral from 1 to 2 of f dot dr. And I did path integrals before. Okay. So imagine that I have right here, I got to stand in the right spot. So I'm going from point 1 to point 2, and I'm just going to go, here's 1, here's 2. I have some force. It doesn't really matter what it is. And I go along this path like this. 1. And I calculate the work. And then I go along a path like this. Path 2. And suppose work 1 plus work 2 equals 0. That means that now that doesn't mean, I caught myself there. What we want is a work integral that depends on the points but not the path. So in this case, if I went backwards, I'd get the same thing. I'd get negative and negative. I went backwards around this loop, right? So, but anyway, the work along this path, the work along that path, if you go in the same direction, would be the same. I'm going to show in another video a generalized version of this that shows that the work does not depend on the path. And then we call that a conservative force. But just because you show for 2 different paths that the work is the same, or that the work around a closed path is 0, that doesn't mean it's true for all paths. We will show all paths later. But it's a good hint that it is conservative. And if it's not 0 work around a closed path, it's definitely not conservative. And when it's conservative, then we can write that as a potential energy instead of a work. And that's really what we want to get to. But today, I'm going to do something. I have 3 different force functions. I have gravitational force, constant gravitational force. I have this one that's just made up, cx hat minus by hat. B is a constant, c is a constant. And then I have this one, negative cy x hat plus cxy hat. And I'm going to calculate the work around a closed path for these 3 cases. I'm going to do it analytically, and then I'm going to do it numerically, which I did before in a previous video. So I'm going to use that code and expand on it. It's going to be fun. Okay, so in this case, in all the cases, we're going to start up here at point 1, which is the point 0, 1, down to 1, 0, and to 0, 0 in the back. So we're going to make that loop. Make that loop. Make that loop. And we're going to calculate. I'm going to do this one, all 3 steps, not too hard. Do that one, all 3 steps. I'm going to do that one, then do it in Python. Do that one and do it in Python. Do it in that one and do it in Python. It's kind of sketched out the fields here. This one kind of, this one looks out like that, right? Because as x gets larger, then the field gets larger. And this one's kind of a weirder shape over there. But let's just get to it. Let's do this one. I'm going to erase everything. I want to keep those 2 forces because I'll forget. Let's call this F1. F2 is C x hat minus B y hat. F3 is negative C y x hat plus C x y hat. So those are my forces. Okay, let's do this first one. So I want to integrate along this closed path, which is actually 3 paths, right? So I can integrate from 1 to 2, and then 2 to 3, and 3 to 1. So I'll say work is the integral from 1 to 2 f dot dr plus the integral from 2 to 3 f dot dr plus the integral from 3 to 1 f dot dr. So in Cartesian coordinates, remember that dr is equal to the vector dx x hat plus dy y hat. The direction of integration comes from the limits of integration, not from your dr vector. Okay. So let's just write this out. So work, we'll call this work 1, is going to be the integral from point 1 to 2 of f, which is negative mg y hat, dot this. So I get negative gm dy. right? That's the dot product between those two. Now, there's nothing in here that only thing in here depends on y. So I can integrate over the limits of y. So I can say this is from y1 to y2. So y1 is 1, y2 is 0. So this is going to be equal to negative mgy from 1 to 0. So this is going to be equal to, let's say this is just, let's say mg is 1. Because I don't want to do any, I don't want to break out the calculator, okay, which I wouldn't have to, but still. So that's going to be negative 1 at 0. So negative 1 times 0 minus negative 1 times 1. So I get 1. So this is going to be 1. Now let's do the next one. The next one, the only thing that changes is the limits of integration, right? I still have the same dr, I still have the same function, but now I have a limits of integration. Now, I'm still in just the y, so I only need y values. So here I'm going to go from y2 to y3. So let's say this is from y2 to y3, which is going to be negative mgy from y2 to y3. And that's going to be equal to 0, 0. So this is 0, 0. And finally, the last thing, all I have to do again is change the limits of integration. I didn't change anything in the problem. So now I'm just going to go from y3 to y1, y3 to y1. So y3 is equal to 1, y1 is equal to 0, and I get negative mg, final. Oh, this is back. Oh, this is, yeah. This is, I knew I was getting it wrong. Negative mg 1 minus 0, so negative 1. So now I have negative 1. So my total work is going to be 1 plus 0 minus 1, 0. The work along the path is 0. And again, that doesn't mean this is the conservative field, because it could be just a particular path that worked. Okay. Let's do this in Python. So remember, in Python, what we're going to do is something a little bit different. I'm going to erase this stuff right here. And I've already did this in the previous video. But if I want to find the work going from point 1 to point 2, I'm going to break it into steps. So if I calculate the vector dr, which is the step size, and I calculate the vector f, I'm going to assume f is constant over that. So delta work for that first step is going to be f dot delta r. So I can calculate the work along a finite step. And then the total work is just going to, along that path, is just going to be the sum of the works along each individual path. Now, there's a couple tricks here. One, I'm going to take this point and that point, and then find a vector between them, and then divide that into n steps. And then I can just move my object along that direction. Another trick I'm going to use is to know when to stop the loop. You could count, right? That'd be one way to do it. Actually, that'd probably be a better way to do it. I didn't count. But what I do is just calculate the distance between my object and the final point, and I keep moving it until that distance is very small. Okay, so I already have the code for this. I just need to add in that, and that's what we're going to do. Switching to Python. Okay, this is the code that I did before. Now, I have point 1 and point 2 already as we have right there. So point 3 is just going to be the origin. Point 3, I'm going to put a sphere there. Position equals vector 0, 0, 0. Radius equals 0.05. Well, I should run this just so you can see what happens. Let's go through this code as it is. So in this, I need to change that force, because this is in the previous problem. So I have my object it's going to move, the ball, and that's my number of steps between the 2 points. Is this big enough? Yeah, I like it a little bit bigger. Scoochie over, okay. This DRR calculates the total vector position from point 1 to point 2, and then I divide it by n steps to get the step size. RF is the distance from the point to the final, and it's used to just stop the loop. Here is my force function. So here I need to change this. Let's just write this as return the vector 0, -1, 0. I'm going to say the force is -1. So this is going to always return -1 in the y direction. That's fine. Okay. Even though I'm going to give it an r value. F scale is just used to draw an arrow. You don't actually have to draw the force arrow, but I'm going to draw the force arrow because I want to. And then here's my work, right? I need to add my work steps to some value, so I need to start with the value of work, and that's 0. And then this is the loop that I'm going to go until it gets to the end. Rate, I'm going to update the position of the ball, calculate the work along that step, add to the total, and then that just draws the arrow and moves the arrow and then finds that. Now I'm going to have to change this, I think, to something smaller so that the arrow works. Let's just see, because I changed the force. Oh, that was too small. Let's put it back at 0.5. Maybe that was fine. Okay, that's fine. Okay. So that's the work done along that path, and you see I get 1. Okay, so now we just need to do this path. Oops, zoomed in too far, and then the other path. So I am just going to do what I do, and that's to copy and paste. So let's call this work 1, and then I'm going to call this work 1, and then I'm going to print work 1. So I can break it up in steps. Now I'm going to copy this whole thing right there, and I'm going to paste it down here. And I'm going to do it for work 2. And then it's going to change this to 2. I'm going to change this to 2. And then I'm going to change this to 2. But I do need to do something. I need to change a couple things. I need to first calculate my new delta r vector. So up here, this. Let's change that. I'm going to copy that. Actually, let's copy this too. I'm going to need to do this stuff. Okay, so here's work 2. Let's just put this right there. This is going to be going from P2 to P3. So this is P3 minus P2. And then this is going to be P3 minus the ball. And that's fine, that's fine. I think everything else is, oh, this needs to be P3. I think that should work. Okay, let's see if it works. Could be terrible error here, you never know. There you go. Okay, so we already said the work along that second path was 0, and we get 0. Now we just need to do that last path. So we're going to repeat the whole thing. And now when I do the other functions, we won't have to copy and paste. We can just change stuff. So I'm going to copy all of this, and I'm going to paste it down here, and I'm going to just update it. So now we're going to do W3, and this is going to be the final position's 1, and we're starting at position 3. We're going 3 to 1. And this is going to be position 1. This is work 3, 3, and this is 1. And this is 3, and this is 3. Let's see if it works. And then let's print out the total. Print W equals W1 plus W2 plus W3. And then I'm going to put the units because I'm a good person. Did I put a dot there? Okay. Let's run this. Looks good. Back up. I didn't quite get to the top just because of the way I did my loop. And I got -0.9, so it's not quite the same. Let's just go ahead and fix this. There's a couple ways to fix this. I'm going to fix this by breaking into 100 steps instead of 10. So in up here is 100. And now the rate I need to increase to faster because I don't have the patience to make it run that long. Okay, let's run it again. I think my problem, I think I need to put these as greater than or equal to. Greater than or equal to. And you have to say things. When you add stuff in there, like, if you don't say it, it doesn't count. Okay. Now let's run it. Look, it's smooth. Slow though. Okay. Close enough. Okay, let's do the next function. Going back to the board. So now in our next function, we're going to use this as our function. So it's going to make things a little bit different. We still have the same, this is all the same. We have the different works. We have to calculate those. So let's just do the first thing. So work 1 is going to be the integral from point 1 to point 2 of f dot dr. So here's f, and there's dr. So I'm going to get c is 1. So I get x dx minus b is 1 minus dy. Well, how do I do that integral? Well, in this case, I can break this into two integrals. I can say the integral from 1 to 2. These are points, x dx minus the integral from 1 to 2 dy. And this only depends on x. This only depends on y. So I can say this is x1, x2, y1, y2. And I can do those integrals. So I get the integral of x dx is going to be x squared over 2 from x1 equals 0 to x2 equals 1, and then minus y from y1 equals 1 to y1 equals 0. So if I do that, I get 1 squared divided by 2 minus 0, so 1/2, and this is going to be minus 0 minus 1, so it's going to be plus 1, so it's 3/2. May have made a mistake there. I'm okay with that. I'm going to put my number up here, 3/2. Okay, you can't even see that. Now let's do the next step. For the next step, the integral is the same, right? But I have different limits of integration. So now instead of going from 1 to 2, I'm going to go from 2 to 3, 2 to 3. I can still do that. And so here, when I'm going from 2 to 3, the x integral goes from 0 to 0. I'm sorry, it goes from 1 to 0. It goes from 1 to 0. The y integral goes from 0 to 0, right? 0 to 0. So that means that this integral is going to be equal to x squared over 2 is going to be 0 minus 1/2. So minus 1/2. I'll put it down here. And then finally, the last integral, I'm going from 3 to 1. So let's just change these limits right here. So here, the x goes from 0 to 0. And here, y goes from 0 to 1. So this evaluation is going to be 0. Did I get 0 before? I didn't get 0. It was x. No, that's right. That was 0. OK, so this is going to be equal to 0 and then minus 1. So I get 3/2 minus 1/2 minus 1/2. It is 0. The total work. Now let's jump over to our code. It's pretty easy to change this, right? All I need to do is to switch to Python. Hello, Python. Up here, what I'm going to do is to change my force function. I put it in there as a function. So this gives the force at that position. And I'm just going to change this to, I'm going to do it the simple way. I said this was x minus 1. So it's going to be rt.x. That's the x component of the vector I passed to it. And then, which is minus 1? Minus 1. Minus 1, 0. So now I changed the force. Let's just go ahead and run it and see what happens. So you'll notice that vector force changes. And here we go. 1.48. So it's close. It's close. It's like very close, right? So these two are negative and that one's positive. I think it's fine. So in this case, the work done along the path is 0, numerically and analytically. Now let's do the last function, which is going to take a little bit of tricks, right? So that's still my dr. Where's my chalk? Okay, there it is. But now I have, this is my function. So work is going to be equal to, the first one's going to be the integral from point 1 to point 2 of f dot dr. So it's going to be negative y dx plus x dy. Now I have a problem. I can still break this into two integrals from point 1 to 2 of negative y dx plus the integral from 1 to 2 x dy. I can still do that, okay? But I can't evaluate those integrals because this has a y and an x. This has an x and a y, and I can't evaluate that integral. So in this case, I'm going to have to actually use the path. I'm going to have to use the equation of the path. So right here, the equation of this line is y equals negative x plus 1, right? Because there's a slope of negative 1, has a y-intercept of 1. So I have that as true. I can use that to substitute in over here for that equation. So work 1 is going to be negative the integral from x1 equals 0 to x2 equals 1. And then I have y, which is negative x plus 1 dx. This integral, I can substitute in my value for x. So x is going to be equal to negative y plus 1. So if I put that in, I get plus the integral from y1 equals 1 to y2 equals 0, negative y plus 1 dy. So now I have an integral that only depends on x. I have an integral that only depends on y. I can actually evaluate those integrals. So this is going to be negative, so positive, x squared over 2 minus x from 0 to 1 plus negative y squared over 2 plus y from 1 to 0. And this is going to give me, let's do this, we're going to get 1/2 minus 1, so it's negative 1/2 minus 0. So negative 1/2. I may make an error here, and if I do, I'm just going to carry on, okay, because I'm trying to do it in short notation. So then this is going to be 0 plus 0 minus negative 1/2, so it's plus 1/2, and then minus 1. So I get minus 1. Final answer. Could be wrong. Okay. Now I want to do the next path right here. Along this path, I have a different equation. What's the equation of this line right here? The equation of this line is y equals 0. So that means that when I make my substitution, I need to redo all this stuff. I can't just substitute in the limits of integration. It's a different path. Okay, so now work 2 is going to be, I can put in y equals 0, because that's what this is. So I get the integral of 0 dx. And then I have plus the integral of 2 to 3 x dy. Okay, but I still have that problem. Well, what's the value for x? Well, x could be anything. What I can do, if y is 0, then dy is 0. So this term is also going to be 0. So the whole work is 0. The work done along that path is 0. You can kind of see that because if y equals 0, there will only be a y component of the force, and we're moving in the x direction. So they're perpendicular to each other. So that's fine. I'm 100% positive on that one. Did my thumbs up work? I can't remember. No. Okay. I'm just procrastinating. Now let's do work 3. Again, we have to evaluate the limits from 3 to 1 of negative y dx. Let's just put it in there. Okay. So I still have this. I'm going from 3 to 1. Over here, what's my equation? My equation is x equals 0. That's the equation of that line, x equals 0. So if I go over here, dx is going to be equal to 0, if x is equal to 0. So this becomes, my dx is 0, so I get the integral of 0 dx. I get negative y times 0. So that's 0. This one's going to be plus the integral from 3 to 1 of 0 dy. So it's also 0. So 0. So the whole thing is -1. But is it? OK, let's go to Python. Again, I don't have to change much, right? Because since I thought ahead and I made this function for the force, I can just change the force function and everything works. So in this case, I can't, what is it? I'm using -cy. So let's do negative rt.y as my x component. My y component is going to be rt.x. Yep, and 0. That's it. Let's run it. There you can see that force changing. That's 0. And then, again, that one's perpendicular to the path, too, so it's 0. You can tell that. And so I get -1, 0, 0, -1. So it agrees. It works. I can't believe it actually works. Now let's go back to the previous case. I want to go back to force 2 and show you that we can change the path. Numerically, it's very, 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 very easy to change the path. So I'm going to enter this formula in for my force 2. Force 2 was RTX, and this is -1. Isn't that right? Yep. OK. And then I'm going to run it just to make sure it's working, and that's what we got before. And it was conservative for that path. It wasn't conservative. It was work 0 for that path, which may or may not be conservative. We don't know. What I want to do is to move, I'm pointing at the screen, I want to move point 3. So I have, this is point 1, this is point 2, point 3. I'm going to move point 3 to somewhere over here. Let's put it at -1, -1. Because if I go up here to the top and just change this to -1, -1, everything works fine, right? Because my displacements are based on where that position is. I don't need to change my code. It'll still do the integral. Let's just run it and see what happens. There it goes. See, along there. Along there. I mean, that's kind of cool, right? And if we look at the total work, it's very, very close to 0 again. So is this actually a conservative force? We don't actually know. We'd have to do every single possible path, or we could do an infinitesimally small path for generic XY values. And that's what we'll do, and I'll derive that in the next video to give you something to look forward to. So again, this is part of my classical mechanics series. If you want to look at more of them, I have a link to the playlist down below. You can go watch all of the videos and make yourself happy, and that's very important. But that's it for now. I'll give you this code down below also. I'll talk to you later.